In the digital era of MP3 players, digital phone standards, digital displays, digital records, and 802 computer communications standards, what happened to analog? Experts in designing integrated circuits meet at the Symposium on Very Large-Scale Integrated Circuits to discuss converting analog to digital signals and embedding them in systems. 4 basic kinds of analog to digital converters are described and their specifications discussed.
The term digital is overwhelming or undermining the importance of analog. So nobody wants to call it digital and analog camera, and perhaps that is unreasonable as part of ordinary language. But in a digital camera, you've got real-life intensity of light, colors falling on a sensor, which is part of any system that interfaces to the real world.
Well, whenever you're looking at A to D converters, one of the questions you have to ask yourself is which ones would you like to use? And so this general plot here illustrates what you might want to consider when you're looking at it. On the x-axis we have conversion rate, and that's the rate of conversion that you need the data converted. And on the y-axis is the resolution in bits. So there's really 4 primary A to D converters that are used. Of course, there are many others that are either derivatives of these or other types, but these are the most commonly used.
One way to understand this is that if we have, let's say, a ruler like this, that's as high as it is, and we give it a voltage that lies, let's say, somewhere over here. So the algorithm or the systematic procedure by which you can encode a piece of electronics to search for that to some accuracy is often called binary search. You proceed by bisecting or halving the full scale. So here's your full scale, here's the midpoint. Now you have to calculate the midpoint. That calculation is being done in analog circuits. It's not yet digital. Now when we bisect it, we decide, does the voltage lie below or above the halfway point? That's a decision. And we give that decision a bit. If it's below, we call it 0. If it's above, we call it 1. Now we can focus, once we've narrowed it down to the lower half of the ruler, on this portion, and we repeat the procedure. We fold this again and we ask ourselves, is it above or below the fold point? In this case it's above. So the second bit is 1 in this case, and we repeat the procedure. In this way you can narrow in on the unknown voltage with a set of zeros and ones that represent the binary decisions above or below.
Like it sounds, it's a successive process of going through, and usually with a binary weighted way of determining each bit in the output of the digital output that comes out. And the SAR useful range is from about 7 to up to maybe 12 bits, and is useful up to about a megasample per second. And so if we want for very, very high speed resolution, or very, very high speed conversion, a flash A to D converter is very often used. It's very useful for resolutions of probably about less than 7 bits. It converts the signal in 1 clock cycle typically. So the data comes in and the data comes out, the digital data comes out all in 1 clock cycle. And we can convert up to about a gigasample or more per second.
The flash A to D converter relies upon a parallel estimation of where the input voltage or signal lies. Imagine this. You want to narrow down the length of something to within 1 centimeter, and you've got 1 meter full scale. Supposing you have 100 people all jam in on the length that you want to measure and put their rulers next to it. But each person is responsible for only measuring 1 centimeter distance. One person measures from 0 to 1, the other one from 1 to 2, the other 2 to 3. They all cram in around this object, push their 100 rulers against it, but they only focus on their 1 centimeter. You can tell right away that one of them will find it immediately. That's a flash A to D converter. It finds the voltage and digitizes it immediately in one cycle. For very high-speed applications, that's the way to go. But it needs 100 rulers. It needs 100 measurements simultaneously. And the efforts of 99 people will be wasted. They'll not produce a useful result. So it's wasteful in hardware. The pipeline A to D converter overcomes that problem. And the way it does it is, it makes a chain gang or a bucket brigade. The object or the voltage to be measured is compared against half the full scale by the first entity. And a decision is made, is it above or below? That decision and the voltage itself is passed on to somebody else. And that second entity searches for whether it's above 1/4 or below 1/4, if it lay in the lower half. And then that entity passes on to a third entity. In this way, there's this chain gang effect where each entity only makes one measurement. Now, what's the advantage of this? When you pass on your decision to the next entity, you're free to accept a new quantity to be measured. So you can take in new quantities after one measurement. At the end of this chain gang, when you look at everybody's decision, you can compile them and you get a measurement of the sample that is propagating down. That's called a pipeline A to D converter. Now, what's interesting about that is that this pipeline takes in a new measurement every cycle, which is the same as the flash, but it doesn't waste the efforts of 100 people. In fact, if you divide up the full scale into 2 to the power n pieces, you only need n entities to make the measurements. So it is a very efficient way. For example, if we go back to our instance of 1 meter being divided into 100 centimeters, we would only need 7 measurements to narrow down to 1 part in 100.
And that one's very suitable for the up to tens to hundreds of megahertz range, or megasamples per second, and in the range of 8 to 12 bits. Typically, you would never see a pipeline converter with more than 14 bits. And finally, the last one is the delta sigma A to D converter. And it's particularly known for being able to convert very high resolution signals. So although the other converters rely on some kind of component matching in order to then resolve the digital output, the delta sigma converter doesn't have that same reliance. And the other thing is it takes the quantization noise and it filters it in a way that it gets shaped out to high frequencies, which allows us to get very, very high resolution. So for a delta sigma converter, they've been demonstrated up to as high as 24, 25 bits, of course for very, very low conversion rate. But for higher conversion rates up to megahertz or megasample per second for in the 12-bit range. So that kind of gives an overview of the 4 primary A to D architectures that are currently used.
So what's interesting is that we see this reversion or closing of the cycle. We start off in the late 60s and early 70s with flash or so-called successive approximation A to D converters. Then in the 80s we see the pipeline A to D converter that becomes sort of the industry standard. And now we see a reversion to flash because the pipeline demands certain components that are not well suited to low voltage operation in these scale technologies, and they don't scale as aggressively. They don't benefit from the scaling as do flash-like devices. So what we see are these cycles.